rho into pi r star OCN. And this is supposed to be G. So I could do rho tensor OX here. and put OX here. So in any case, whatever whatever I should have written here exactly, this guy here is a representation of G. Right? So it splits into isotypical components. So just think of the idempotence of the representation theory of G. If I take the ring CG, right? This is a direct sum of subrings generated by idempotency rho. So projector or idempotence. Or projectors. Right? And so any representation of G splits up in a canonical way into these direct sum of E rows. So I'm not splitting these up into irreducible components. I'm splitting them up into very big isotypical things. And so what I'm saying is here, take rho. Rho may be, for example, a two-dimensional vector space with an action of G. I have to map that forward into two elements here so that the map is equivariant, so that when I move them around here according to G, these guys move around in the same way according to G. It's better if I come to an example because I haven't given a very clean definition. Right, so this is Cn with the original group action. Right, it's just this polynomial ring. Right, this thing here now, I've separated out. This guy here is an OX module without, and G acts trivially, no G action. Right, whereas this thing here is a G action, a G module. And there's no OX action. The tensor product, of course, just takes place over C. Right, and so here I'm going to have these F rho here. And so F rho on Y is, so let me call this map phi, resolution of singularities. So I'm going to write down phi upper star of F primed Y, F primed rho, right, and then divided by torsion. Right, so this is so quite typically this F primed rho here will not be a locally free sheaf. It'll almost never be a locally free sheaf on X. Right, and so here I'm doing this phi upper star of F primed rho divided by torsion, and I say that these guys here are locally free. So Hilb, this G Hilb. Okay, I've told you what cluster is. I've told you what G Hilb parametrizes, but I haven't told you what he is. So G Hilb of Cn is the Hilbert scheme of G clusters. So as a set, it's the set of Z in Cn subschemes with the properties I had here. Okay, with these, with property star. So, you know, this means that they're invariant under G, and another way of saying this is it's an ideal sheaf. Each one of these Z's has an ideal sheaf like this. Goes to OCN, goes to OZ. Right? And this guy here is a vector subspace G invariant and of codimension G, codimension the order of G. Okay? Now, and there's an ideal. So I want this not just to be a set, but I want it to be a scheme. Right? And so what I do is I take this to be a subscheme of, so take the subscheme, take for its scheme structure consider IZ in OCN in the Grassmannian of OCN codimension G. So this is linear vector subspaces. Okay, so this is sort of a little bit infinite dimensional. I'm asking for vector subspaces of this slightly infinite dimensional space of the given codimension, right? And you can prove quite easily that every such subscheme here, every IZ, is determined by its intersection with the polynomials of degree less than. So you can work with polynomials of degree less than, let me say, just to be safe, let me say less than or equal to G plus 1. Yeah? And so I say this is IZ, this is linear subspaces inside, vector subspaces inside this infinite dimensional space. But in fact, if we just restrict this to polynomials of degree less than G plus 1, then if I know this guy IZ in there, and I know that he's an ideal of OCN, then he's determined by what happens in these degrees, right? And so this is the set of G clusters, the IZ satisfying these conditions are a closed subscheme. Of this Grassmannian. So I'm doing Grassmannian. Now I'm writing OCN, but I'm really taking polynomials of degree less than n plus 1, G plus 1, and then G. So subspaces of this. So that, you know, I'm really writing down C of U1 up to UN of degree less than or equal to this fixed bound G plus 1. Yeah, and so inside here, I look at things with I look at vector subspaces of this codimension that generate an ideal IZ satisfying the above conditions, right? And that's a closed subscheme. Okay. However, you know, if you want, this is a construction of the Hilbert scheme. And what properties does this Hilbert scheme have? So the Hilbert scheme has the universal property that these sheaves F row, described over there, are locally free. So in other words, if I'm standing at a point OZ here, right, I've got this OCN mapping to OZ, and as far as Cn is concerned, the kernel there is going to be some singular object, but up on so the thing I'm really doing is I'm really blowing up all the usually singular sheaves, tautological sheaves, F primed row to locally free sheaves. Yeah. Sorry, I'm not explaining this very well, but what I say is true. So, namely, the Hilbert. If I write, so I'm not choosing a resolution here. Here at the moment, I'm describing. So, G Hilb of Cn has a morphism to Cn, so Cn over G. It's called the Hilbert-Chow morphism. Right, and then over this I have this tautological structure which is called O curly Z. So Z is in curly Z is contained in Cn cross the Hilbert scheme. Right. So at a point here, I get a cluster Z contained in Cn. Right. This has two projections, and its fibre over this projection is these Z. Right. And by construction, this guy here, over every fibre, over every point of Cn, this fibre Z has the same rank however many components of the irreducible. So this Z restricted to the fibre over G Hilb over Z in G Hilb is the regular representation CG. Yeah. Sorry, it's probably more convincing to do an example. Okay, so in any case, these guys, Gonzalez, Springberg, and Verdier, used these F row to give a basis of H0 of Y Z dual to the basis EI is H2. Yes? And in fact, because these are Chern classes of vector bundles, they also do K-theory of Y. So I'll come back to this next time, but we're very close to here, these arguments involving derived category. So I haven't left myself very much time, but I want to give a calculation of a G Hilbert scheme, and I want to remind you of a very pleasant and a very useful and productive method of calculating. So I want to calculate G Hilb of C2, where G is the abelian group (1/19) of 1,7. Right, so this is of course not in SL2, this is in GL2. So my point of doing this is I want to remind you all that you're supposed to know Hirzebruch-Young continued fractions, right? So I will use these comprehensively on Saturday. I'll use these hundreds of times. So Hirzebruch-Young continued fractions. So in this case, this is a very, very simple thing. If I write down 19 divided by 7, I get, this is 3 minus 1 over 4 minus 1 over 2. Yes? And I want to tell a story about this, and the story goes like this. So let's look at the lattice Z2, right, with basis like this, and I want to write Z2 plus Z times this 1/19 of 1/7. Okay, so the thing I want to calculate is the lattice points in this unit cube. Right, so this is a lattice Z2, this is a bigger lattice, L. This is a slightly bigger lattice, a finite index over Z2, right? And what are we supposed to do? Well, I chose this point 1,7, so 1, have I done this exactly wrong? I want this 1,7 to be the point with the smallest okay, so it's down here somewhere. It's the point with the smallest x coordinate. Right, its x coordinate is 1/19, so I've probably drawn it too big in that direction. Yeah? And so the calculation goes like this. Let me write P0. I want to write E2 for the point 0, 1. And I'm really thinking of it as 1/19 of 0,19. Right? And then I write this point E. Let me write this point P1. P1 is 1/19 of 1/7. So let's just forget about the denominators. Yeah? And so the thing I want to draw is this. Right, I want to find a point P2 here. And I'm doing this P2 according to, first of all, this 3. Right, so I'm going to do 3 times him minus 1 of him. So I'm going to get P2 here. That's 3 times this guy minus 1 times this guy. Right, so that's 3, 2. Right, so this is the P2. 3, 2. So, you know, as you can see, it's got x coordinate a bit more than twice, a bit more than P1, a bit more than twice of P1. Right? And then, so I want to continue this. I want to do this one times 4 minus him. Right? So the thing I'm doing here is 3 times this 7 is just a bit bigger than 19, and 4 times this 2 is just a bit bigger than 7. So that's exactly what happens when you calculate here. Right? So this gives P3 is, so I'm doing this times 4 minus 1. I'm getting 11 here. Right? Times 4 minus 1, I'm getting 1 there. Right? And then if I do this times 2 and subtract off, I get this point P4, which is just E1. Yes? And so this is now, I'm doing twice of this minus this, so I'm getting 19, 0. Right? And remember, the 1/19 was going throughout here, and so this is the point here. So the thing I've calculated is this convex hull of the lattice points here. So this is a Newton polygon or a convex hull of lattice points. Right, so every lattice point in this first cube, every lattice point in the whole of the first quadrant is a linear combination of these guys. Yes? So look, next time I'm going to be using this calculation 100 times, and I want you to know what's going on here. So this is a completely general phenomenon. If you look at, on my website, I've got a little set of notes called Cyclic Quotient Singularities of Surfaces, and it explains how to do this and explains lots of theory associated with it. Okay? So let's take this as read. I know this. So the thing I'm writing down here really is I'm thinking 3. That means this line here has to break. This line has to break by a factor of 3. So here I'm doing this times 3, take away 1. Right? And this line here, it's breaking by a 4. There's these little tags here. They're telling me how to maneuver. As I drive down there, it says turn the wheel to the left by that amount, and then turn the wheel to the left by that amount. Yes? And then here, because I've got 2, it means that these points here are in arithmetic progression. So this point here is the average of these 2. Okay, so what's this got to do with Hilbert's scheme? So I say that Y is G Hilb of C2 is this picture. Right? And so here it's traditional to put minus 3, minus 4, minus 2 here. These are the original coordinates of C2. So here I have, this guy here is resolving C2 divided by this group G, right? And the C2 has coordinate axes here. These are not exceptional curves. This is just part of these are toric strata of the original C2. Right? And now what's this? Where are my clusters here? So I look at this. If I look at these 2 vectors, they form a basis of this lattice L. So any 2 consecutive vectors around the Newton boundary form a basis for the lattice L. Right? And there's a dual basis in the lattice of monomials. And the dual basis in the lattice of monomials is the thing that... So I want to look at 0, 19, 1, 7. And maybe I want to look at my notes as well. So here I'm going to, I'm looking at this. I'm going to write x to the 19th equals a, and y equals b, x to the 7th. Yes? And I say that AB here are coordinates on this thing here, which is y0. Yes, and so this is the x-axis. This is the thing that remains of the x-axis after dividing out by the group action, and it's parametrized by x, except that x is not invariant, so I have to take x to the 19th. Right? This ratio y to x to the 7, y and x to the 7 belong to the same eigenvalue of the group action. Right? The group acts on x by epsilon, and it acts on y by epsilon to the 7th. So therefore this ratio here is invariant. Right? So when a and b are 0, this is defining this point. When b is 0, it's defining points up there. And when b is not equal to 0, and maybe a is 0, it's defining points along here. Right? So this line here is the line P1 with coordinates y to x to the 7th. Right? Now, so I'm going to do the same thing with the others, with a little bit less gesticulation. Right? So here I'm going to get x to the 7th equals b times y, and a times y cubed equals b times x squared. And now I need another function, right? So I'm going to write down x to the 5th y squared equals ab. Right, let me just continue the calculation here without any more explanation. So 3, 2, 11, 1, thus x squared equals ay cubed, y to the 11th equals bx, and x y to the 8th is ab. And the last one is x equals a y to the 11th, y to the 19th equals b. Right, and so the thing I'm doing here is I'm writing down 4 copies of C2 with parameters AB. So, if you were doing it properly, these would be A0, B0, A1, B1, A2, B2, A3, B3, and so on. Right? But let's look at each of these little boxes. So let's look in particular at this box. Right? So what is the scheme defined by x to the 7th equals ay, and y cubed equals bx squared, and x to the 5th y squared equals ab. Okay? So I say this is a cluster. I say this is a cluster for a G cluster for the group. Right? So what I'm going to do is, let's call this the ideal generated by these guys to be I7. Right, so let's write OZ is polynomial ring in X and Y. They should be U and V to be consistent with previous stuff. But anyway, IZ. Right? And this is based over C by, so I'm going to write down 1x squared up to x to the 6th. And when I get to x to the 7th, I'm not going to bother. Right? I'm going to say, instead of writing x to the 7th here, I'm going to write down an equation for x to the 7th and write box. Right? So x to the 7th here is a linear combination of y, and I want to use y here. Yes? And so I've also got y squared. When I get to y cubed, I don't bother. Right? And now here I've got xy, x squared y, and so on, all the way up to x to the 4th y, and then I've got a little equation for x to the 5th y. Right? And there are no other equations here, so I've got x squared y squared, and so on, all the way up to x to the 4th y squared. Right? So I have a little box like this, right, which is really 7 times 3 minus 2. Yeah? So 7 times 3, and then I'm saying I don't need these two monomials. Should be 7. Anyway. So let's count the monomials. There's 7 here. I'm sorry, I'm confusing myself. Yes, okay. There's 7 monomials here, and there's 5 there, and there's 5 there, so it makes 19. Sorry, there's a little mistake of arithmetic going on here that I'm not completely following. Oh, I'm sorry, something stupid. Right, the equation is there. The equation is x to the 5th y squared. Right, so the thing this picture is correct. Right, I've got 7 along there, 7 along there, and 5 along there. Yeah, and you can check that I have the regular representation of G. So in this case, G is an abelian group, so group of order 19. So the representation theory of an abelian group of order 19 we know perfectly well. It's got 19 characters. And so if you think about what I've got here, I've got the character 0, 1, 2, 3, 4, 5, 6, 7, 8 up to I've got 0 up to 6, 8 up to 14, and then 14, 15, 16, 17, 18, 18, and then I'm back to 19. Yes? So the point is this Z is a G cluster. Right? So I'm going to be doing lots of these in 3 dimensions and in higher dimensions next week. But absolutely everything is based on this idea of doing Hitzbrook-Young continued fractions. You better know how to do them and know how to do them in your, immediately without hesitation. Okay, so the point here is that if you want to make the quotient by this group action and think of it as an algebraic variety, in other words, throw away the group action, you can take it's a surface with rational singularities, so you can make a resolution of singularities just by blowing up. Right? Forget everything about the quotient and make the blow up. Right? This is a completely different idea. The idea here is let's look at C2. Let's look on C2 with this equivariant geometry of C at some special moduli problem. Right? The moduli problem is the moduli problem of these clusters. Right? And by doing this calculation here, I find every G cluster. So look, the rules here are very simple. The rule is going to be that OZ is supposed to be isomorphic to C of G. Right? For an abelian group, this is direct sum of 1 times every one-dimensional representation. Right? And so here, when I'm seeing y cubed and x squared, and y, remember, the representation is 1, 7. So y cubed is in the representation epsilon to the power of 21, and that's the same as this epsilon squared. Right? And so I've got to choose, in every cluster, I've got to choose either I have y cubed as a basis element, or I have x squared as a basis element, or both. The B can be non-zero. Right? However, if I've chosen this guy to be a basis element, then I must have a relation saying y cubed is a multiple of him. Right? And so every one of these relations here is forced. I must have, in every cluster, I must have x to the 19th as a constant, so x to the 19th has to be some multiple of a constant in the field. Right? That's just coming from this. And it's also coming from this stuff I was trying to say here about the Hilbert scheme is the universal solution to finding locally free sheaves, to making these Fs into locally free sheaves. Okay, I'm sorry I've gone slightly over time.